So 1/2 apothem times perimeter. All right. So for this first one, they actually give you everything that you need. If you'll recall, the apothem is the distance from the center perpendicular to the side. So we have the distance from the center perpendicular to the side, and they've given that to us. They've given us this distance right here. All right. The perimeter, while they didn't give us the perimeter, they gave us what we needed to find the perimeter. The perimeter is going to be one side, which is 8, times the number of sides, which also happens to be 8. So the perimeter here is going to be 64. Side length times the number of sides. And then once you have that, you're just going to plug it into your formula that you know, which is 1/2 apothem, 9.7 times perimeter, which is 64. And when you do that, you will get, rounded to one decimal place, 310.4. And that is square units. They didn't give us units, but if they had, we would have used that. Oh, potentially. So remember we talked about these interior angles here. And so if I were to create this isosceles triangle right there, if I were to draw all of them, I would have 6 of them. So to figure out what this angle measure is, I would just take 360 divided by my number of sides, which means that entire angle is 60. So for the triangle that I'm actually looking at, which is this triangle right here, I just need this little tiny piece, which is half. So this is going to be my 30. This is my 60, and that's a 90. So I have a 30, 60, 90 triangle. And I know the longer leg of the 30, 60, 90 triangle, all right, which is 8. So my apothem here is also the longer leg of my 30, 60, 90 triangle. What I need is the shorter leg of my 30, 60, 90 triangle. And so this is where it's very important to remember that if this is what I'm looking for, this side is going to be that times the square root of 3. That's going to be that if I were to need that as well. All right, so I'm going to take this 8, and to solve for x, I would divide by the square root of 3. All right, so that means this piece of it right here is going to be 8 divided by the square root of 3, correct? That's only half of my side length though, so I have to double it in order to get the entire side length. And we talked about multiplying. To double it, you just multiply the number that's not in, right? So it's going to be 16 over the square root of 3. That's my entire side length, okay? My entire side length is 16 over the square root of 3. Now I don't need my side length, I need my perimeter. So what do I need to do then to find my perimeter, which is what I actually need for my formula? Side length times what? Number of sides, right? How many sides do I have? 6. So my perimeter here is going to be 6 times my side length. That's my perimeter. Now, you do not need to, in the process, plug it in and round, plug it in and round, plug it in and round. You can leave it just like that if you want to, or you can multiply the 6 and the 16, 96 there if you want to. All right? But you need to plug all of that back into your formula. 1/2 apothem times your perimeter. Okay, so in your calculator, you can do all of this, all right? You can say 0.5 times 8 times 96 divided by the square root of 3. You can do that in your calculators. And when you do that, you should get 221.7 square units, rounded to the nearest tenth, all right? So you are just using these special right triangles to get what you need to then solve for your area of your regular polygon. So this required a 30, 60, 90, as did 5. 5 also required a 30, 60, 90, just a little bit differently. All right, let's look at the next one. There's actually 2 ways to solve this next one. I'm going to show you both. Right, so I'm going to create the central triangles. I'm going to go to my center. And I'm going to create these central triangles here. Remember, they go to the vertices, okay? All right, now, this means that I'm going to cut one of those in half. Those are all isosceles triangles. So I'm going to take one of these and cut it in half here, okay? Which means this right here is 6, all right? This is my hypotenuse. All right, and this is my apothem, which is what I'm trying to find, okay? My apothem is what I'm trying to find. Now, in this case, I only had 3 internal angles because I have 3 sides, which means I take 360 divided by 3, which gives me 120. So this big, huge angle is 120. So when I cut it in half, this is my 60. Which means on this case, my apothem is my short side. All right? Whereas on the other one, my apothem was the long side of my special right triangle. This is the shorter leg. Actually, this is the apothem here is the shorter leg, okay? So you have to pay attention to which one is across from that 60. That's going to be the longer leg that is, side square 3, all right? So there's actually 2 ways to do this. I can find my apothem, which is going to just be, this is my longer side. My longer side equals my shorter side times the square root of 3. So once again, I'll divide by the square root of 3. So this guy right here is going to be 6 divided by the square root of 3. So I have my apothem, which is 6 over the square root of 3. Okay? And so if I want to at this point, I can go ahead and do my 1/2 apothem, 6 over the square root of 3, times my perimeter. Well, one of my side lengths is 12. It is a triangle, so what is my perimeter? Triangle with one side length of 12. 3 times 12, right? 36. There we go. All right. So that's all we do, and we can put it into our calculators, and you will get 62.4. Now, you could solve for the hypotenuse, which is also going to be this guy right here. All right, which means you could double the short side. So this is 6 square root of 3. This piece of it is 12 square root of 3, which means this is your height. And you could say 1/2 base times height if you wanted to. But you've already got everything you need when you figure this guy out, so you might as well just plug it into the regular polygon, 1/2 apothem times perimeter, okay? But if you forget the 1/2 apothem times perimeter, but somehow remember your special right triangles, you can do 1/2 base times height as well. All right. So those two required 30, 60, 90. Those two required 30, 60, 90. Okay. The last one actually is going to be a 45, 45, 90. So let's look at the square here. With the square, I don't even have to take 360 and do any of that, because honestly, I know that this corner right here is 90 degrees. And it's cut it in half. So I already know this is a 45, 45, 90. Okay, and keep in mind that 8 square root of 6 is my hypotenuse. Okay, that is my hypotenuse. You did not have that little line already drawn. That 8 square root of 6 is my hypotenuse. Now remember, on a 45, 45, 90 triangle, these side lengths are the same, and this hypotenuse is side times the square root of 2. So that means my hypotenuse, which is 8 square root of 6, equals my side length that I'm trying to figure out, square root of 2. Okay? So then how do I solve for my side length? Well, I divide by the square root of 2. Both sides are divided by the square root of 2. Now, this is why we did this yesterday. If I have a root over a root, I can reduce them. I can reduce what's inside, and I can reduce what's outside. I just can't reduce from outside to inside. Well, you can see that 6 over 2 reduces, yes? 6 is divisible by 2. 2 is divisible by 2. The square root of 1 is just 1. So I end up with an 8 square root of 3 as my piece of my side length here, right? Piece of my side length here. Everybody see that? So I can do this one of 2 ways. I can do this 1/2 apothem times perimeter if I want to, but it's a square. So if I have half of my side length as 8 square root of 3. My entire side length is just that doubled. So the entire side length here is just going to be 16 square root of 3, right? 16 square root of 3. And what's my formula for a square when I have a side length? It's just side times side, yes? That's the area of a square. So side times side. And you're going to get 768 when you do that. Side times side. So if you have an easier formula like a square, just figure out what your side is and use your square formula. Now, any of the regular polygons, you can use 1/2 apothem times perimeter, even if it doesn't have another one, or if it does, it doesn't matter. Square, triangle, if it's a regular polygon, you can use 1/2 apothem times perimeter. But if it's an easier formula, just use the easier formula. We have done regular polygons, 1/2 apothem times perimeter, and they show this progression here. We have a 3-sided, 4, 5, 6, 7, 8, so on and so forth. And you can see that they all work 1/2 the apothem times the perimeter, okay? 1/2 the apothem times the perimeter. And so how this progresses then for a circle is the apothem for a circle is the same thing as the radius. That's not true for a regular polygon. The radius is actually a different length for a regular polygon. But the more sides you add to a polygon, the closer you get to an actual circle, right? You can see that these polygons are getting to look more and more and more like a circle. You can only imagine what a 20-sided polygon would look like. It would be impossible for me to draw it, right? But a 20-sided polygon would look very much like a circle. And so when you get closer and closer to a circle, your radius and your apothem get closer and closer in length. And then by the time you get to a circle, the radius and the apothem are really the same thing. And so instead of saying 1/2 apothem, for a circle, it's 1/2 the radius, because it is the apothem. Well, instead of perimeter, for a circle, we call that circumference, okay? So perimeter for a polygon is the same thing as circumference for a circle. And so then we get this formula. We're going to take the 1/2 radius times circumference, and we're going to plug in what circumference is. Circumference is 2 pi r. Hopefully a formula you already know. 2 pi r is circumference. So we're just going to plug that in for circumference because that's what it is for a circle. And so you have 1/2 your radius times your circumference, which is 2 pi r. Well, the 1/2 and the 2 cancel out to 1. R times r is r squared. And you get this very familiar area of a circle, pi r squared. It comes from the same formula as a regular polygon. Comes from the same formula. So for a circle, the area of a circle is pi times the square of the radius, pi r squared. All right, which means if you have the diameter, you need to cut it in half. Whereas for circumference, you can use the diameter. For area, you cannot. You must have the radius, which is half of the diameter. All right, pi r squared. Hopefully one of the easiest ones for you to remember because it's one you've seen for a couple years now. So let's look at this first example. Find the circumference and area of a circle whose diameter is 10 meters. State both the exact value and the decimal approximations to the nearest tenth. So now when they say exact value, when we're talking about a circle, what they mean by exact is leave pi in your answer. If they say round to the nearest whatever, then they want you to plug pi into your calculator. I will say I don't want you to use 3.14. I know that's an approximation for pi, but pi is non-terminating, non-repeating. So use the pi value in your calculator because the more you do with it, the further away from the actual answer you will get if you round it, okay? So because we have the technology to get even closer decimals than 2, we're going to use pi in the calculator, not 3.14, okay? So they want the exact and the decimal. So we're just going to plug it in. The area is pi r squared. They gave me diameter. If my diameter equals 10 meters, what is my radius? All right, so 5 meters. Area, that's rather easy. An exact area would be pi times 5 squared. So 25 pi. This is what they mean by exact. 25 pi is my exact value. All right. If I want the decimal approximation to the nearest tenth, you're going to go into your calculators. You're going to say 25 times pi. All right. And so pi sometimes on your calculator will be a button that is already there. Sometimes you'll have to use a shift or a second depending on what you have. All right. So when you plug it in, you get approximately 78.5. So when you plug it into your calculator, 78.5 square meters versus 25 pi square meters. So this is your rounded. So when you see exact, they want pi. When you see rounded, they want you to plug it in. All right. So let's try a couple of them. So we did central angles with polygons and we divided it 360 by how many sides they have. With central angles for a circle, you do not have a side to think about. So the central angle of a circle is an angle whose vertex is the center of the circle and whose sides contain radii of the circle. So a central angle here would be this. This right here would be a central angle. The center of the circle is the vertex. The sides are the radii. Okay. A sector of a circle is the region bounded by two radii and the intercepted arc. So this is considered a sector. Looks like a piece of pie. All right, that is a sector. A segment of a circle is the region bounded by a chord and its intercepted arc. A chord is a line that goes from one point on the circle to the other. So the most familiar chord that you have used is diameter. Diameter goes all the way across and through the center. That is one type of chord, but this is also another type of chord. Any 2 points on the circle create a chord, okay? And this little part right here is called the segment. It is bounded by the intercepted arc here and a chord, all right? So that is a segment. So you need to know that because we're about to talk about how they use these. You will see pie charts all the time, especially in like a standardized test. They like pie charts. So this is an example of a pie chart. An investor anticipating retirement in 15 years diversifies his portfolio as illustrated. And so we have this domestic stocks here. That is 45% of it. We have foreign stocks. We have bonds and we have cash. All right. Now, when we're talking about the central angle, we are talking about which piece of the circle we have. They have given it to us in percentages, all right? They've given it into percentages, and they want us to determine the central angle for each sector, all right? So we're going to look at each sector, and we're going to say what is the central angle for that sector. Sector meaning the piece of the pie that they've given us, all right? So we're going to look at cash. Well, cash is 5%, all right? How big is a circle in degrees? How big is a circle? Yeah, it's 360 degrees. So if I want to find out what 5% of a circle is, I am going to take 5%, written in decimal form as 0.05, times the entire 360. 0.05 times the entire 360. So that central angle is 18 degrees. 18 degrees. Does that make sense? And I'm going to do that for all of these, all right? So I have bonds here. Well, bonds is 20%. So to find out what that central angle is, it's 20% of an entire circle. So this guy's going to be 72 degrees. Foreign stocks, that's 30%. So I'm going to do the same thing here, 0.30 times my 360 degrees. And then my domestic stock, that one is 45%. So I'm going to do that with this guy. All right. So that's what the central angles would be. If I wanted to know what the actual angle measurement is here, that's 162 degrees. That's my angle measure. All right. The next question wants me to do that, but in the actual dollar amount. The entire portfolio is worth $750,000. So what is each portion? How much does he have invested for each portion? I'm going to take now the dollar amount and multiply it by the percentages. So I'm going to take, for domestic stocks, 45% of the $750,000. And I'm going to get how much money he has in domestic stock. So when you're talking about the pieces of the pie chart, they should all add up to the entire amount. And so if I were to take all of these and add them up, degrees, they should add up to 360. My portfolio dollars should all add up to 750,000 because it should have the entire circle should be accounted for based on each piece of it. All right. So let's try one of those. Flip back over to page 336. Given the U.S. federal spending for 2015 was that ginormous number, 3,760, I don't know, 3,760 billion. That's a lot. No, yeah, billion, million. To the nearest billionth, so just round to the whole there. They've divided into education, other welfare, defense, pension, and health care. All right, they've only chosen 4 of them. All right, but they want you to give the angle measure and I believe the dollar amount for both of them. All right. So you want the angle measure for those 4 and the dollar amount for those 4. And by the way, you can do it because this is in billion. You can just take the 3760, that part of it, this part of it right here, and multiply it. You can leave off the other zeros and just write the word billion after it. Okay. So just take the 3,760, multiply it by your percentages, and just write the word billion. That's what those zeros represent. So we want just this piece of the circle. We want to know how much area of the pie we have. The entire pie would be pi r squared, because that is the area of a circle. But we just have part of the circle. So we basically take pi r squared, and we are going to multiply it by what portion of the circle we have, okay? So we say, well, whatever my angle is, theta, by the way, is a Greek letter. Theta is what they have used. It's just a variable for the angle measure. That is out of how many degrees in a circle? So if I have a part of the circle, it is out of how many degrees in a total circle? What are my number of degrees in a total circle? Cade, how many degrees are in a circle? An entire circle. 360. So we have a portion of a circle. We have a small piece out of 360. So we're going to take that proportion, that ratio, and multiply it by the whole circle. So if I have a fourth of the circle, I'm going to say 1/4 of pi r squared. If I have a third of the circle, I'm going to say a third of pi r squared, okay? And so that's how we come up with this formula, which they've given us for the area of a sector. You do need to know this formula. It is theta. That is just your angle measure over 360 times pi r squared, which is your circle measure, okay? All right, so your angle measure over 360 times pi r squared. So let's look at the example on the next page. They have two things they want us to find. The first thing they want us to find is the area of the sector PRQ. So the entire area of the sector is this pie piece, okay? This is the entire area of the sector. That's what they want us to find first, okay? So we are just going to plug that in to our formula. Our formula is theta. What is the degree measure of this central angle that they gave us? What's that degree measure? Faith, what's the degree measure they gave us here for this particular one? 84. So it's 84 out of 360. All right. And then pi, what is my radius, Bella? What's my radius from my center to the side?
3 centimeters.
Yeah, it's just 3 centimeters. So 3 squared. So 84 out of 360, pi r squared. That's my formula, all right? In this case, they just want us to round to the nearest decimal place, 1 decimal place. So you can literally just plug that in. So 6.6 centimeters squared. They want the exact value there, 6.6 centimeters squared. All right, that's the whole thing. That's the entire thing, okay? The next thing they're asking for is the segment. Now, for the segment, they just want this part right here. So what I can do is I can take that entire piece that I just found, which is this entire pie piece, and I can subtract out this triangle. Right? Yes? And then I would have what's left over. So let's look at the triangle. That's what we need. We need to subtract that. So we're going to take the triangle and we're going to subtract it from what we just found. So let's look at this triangle. We already know that this side length is 3 centimeters. We know that this side length is 4 centimeters. I actually know the other side length. Why? Yeah, they're congruent. It's a radius, right? And every radius in the circle is the same. So this is going to be 3 centimeters as well. So I have an isosceles triangle. And so I can figure out what my height is to do 1/2 base times height. Really, I can just use the Pythagorean Theorem here. All right, so if I were to cut this guy in half, right? It's an isosceles triangle. So that means I can figure out that height because I have 2 and 3. I have a leg and a hypotenuse. So I can say a squared plus b squared equals c squared. B squared equals 5. B equals the square root of 5. All right. So I have a base of 4 and a height as square root of 5 for a triangle. My formula for a triangle is 1/2 base times height. So if I take my entire piece of pie and subtract out my triangle, I will get the segment that's left over. All right, and once again, they won't exact, so you're just plugging this into your calculator. And when you take the 6.6 and subtract your triangle, you should get 2.1 centimeters squared. These are both areas, so they are both square units here. So the entire piece is 6.6, just the segment is 2.1.